a black hole the size of a city, and another that could swallow our entire solar system. They both exist, and they both obey the same equations. But here's the crazy part. The bigger they get, the less dangerous they feel at the edge. We start small, stellar small. Dr. Lena Ortiz spends her nights hunting ghosts. She grew up under polluted skies in Santiago. On weekends, her father would drive her into the Atacama Desert. She'd see the Milky Way as a white river overhead and think, how much is hiding behind that light? Years later, she works at a mountaintop observatory, looking for things that don't want to be seen, like a star orbiting nothing. If a visible star orbits something dark, massive, and compact, and you can't see it in any wavelength, you might be looking at a stellar mass black hole, a corpse of a massive star. A star maybe 20 or 30 times, the sun's mass burns all its fuel, collapses, and explodes as a supernova. If the leftover core is heavy enough, it collapses past the neutron star stage into a black hole. A typical stellar black hole, 3 to maybe a few dozen solar masses. Some formed by mergers can go up to around 100. The size of the event horizon, about 3 kilometers per solar mass. So a 10 solar mass black hole has a horizon the 30 kilometers across. That's a whole sun crushed into something smaller than a city. Lena jokes with her students. Take the sun, shrink it until it fits inside your daily commute. That's a baby black hole. Then she lowers her voice. And that baby could tear you apart kilometers away. Lena still gets goosebumps when she finds a new candidate. It's like discovering a hole in reality, she confesses to a colleague after confirming her latest find. Something that shouldn't exist, but does. I sometimes wake up at night thinking about what it would be like to fall into one. What would you see in those final moments? But the story doesn't stop at cities. It scales violently. Dr. Arun Patel doesn't look through telescopes. He listens to space-time. He grew up in Mumbai, loving bass drops and the rhythm of trains. Then, in college, he heard history. 2 black holes colliding, converted into sound. A faint whoop. His father was deaf. He taught me that feeling vibrations was another kind of hearing, Arun says later. So when I learned we could feel the vibrations of space-time itself, I was hooked. Now he works with gravitational wave detectors like LIGO and Virgo. Instead of light, they measure distance, absurdly small changes in distance, as passing gravitational waves stretch and squeeze space-time. When 2 stellar black holes orbit each other, they lose energy as gravitational waves. They spiral closer, faster, until they merge. In 2015, LIGO detected GW 15914, 2 black holes about 36 and 29 solar masses, merging into one of 62 solar masses. Roughly 3 solar masses worth of energy went out as gravitational waves in 0.2 of a second. For that instant, that merger was more powerful than all the stars in the observable universe in gravitational radiation. From the pitch and shape of these chirps, Arun can tell the masses. Most events are in the 10 to 50 solar mass range, but some signals hint at something bigger. Mergers leaving behind black holes, 100, 200 solar masses. Too big to be ordinary stellar remnants. Too small to be the monsters at galaxy centers. These are candidates for the missing middle. Intermediate mass black holes. Like teenagers between stellar kids and supermassive adults. And we've rarely seen them. It's like finding plenty of children and plenty of adults, Arun tells a colleague over lunch, but almost no teenagers. Either teenagers are hiding or something strange is happening during that growth phase. Some of these teens might be born from repeated mergers in dense star clusters. Others might be ancient seeds from the early universe. Either way, they're the first step on a terrifying size ladder. Professor Ada Mensah lives at the top of that ladder. She grew up in Accra, Ghana. When her father died, she coped by escaping into books about space. Black holes especially, things so heavy that even grief could not escape. I was 12 when he died, she tells a struggling grad student. I remember reading that inside a black hole, time behaves differently. I used to imagine that somewhere, beyond the event horizon, time hadn't passed for him. It wasn't good physics, but it made me want to understand these objects that could bend even time itself. Now she studies black holes in galactic centers. Her domain is the opposite of Lena's city-sized ghosts. Ada studies black holes that could swallow solar systems whole. At the heart of our Milky Way sits Sagittarius A, about 4 million times the mass of the Sun. Its event horizon is about 12 million kilometers across. Huge, but still well inside Mercury's orbit. In other galaxies, Ada infers black holes hundreds of millions or billions of times the Sun's mass. Their event horizons could easily engulf the entire orbit of Pluto. And then there are the true outliers. Objects like the black hole in TON 618, estimated at around 66 billion solar masses. Its event horizon would span roughly 200 billion kilometers, more than 30 times the radius of Pluto's orbit. Our entire solar system would fit comfortably inside that shadow. Ada stares at her simulations and asks the question that keeps her awake at night. How do you grow something that big in the age of the universe we have? Because there's a catch. When gas falls into a black hole, it heats and shines. If you feed too fast, radiation pushes back, blowing material away. That balance is called the Eddington limit. Accreting at that limit, a black hole can roughly double its mass every 45 million years. To go from a 100 solar mass seed to a billion solar mass monster at that rate takes around 800 million years. But we see quasars with billion solar mass black holes less than a billion years after the Big Bang. Very tight timing. So either they started heavier or sometimes broke the rules and ate faster than the Eddington limit allows. Or our picture of their growth is missing a chapter. Ada's simulations show that when galaxies merge, gas can funnel into the center in huge, brief feeding frenzies. Black holes can gorge, not sip. Still, some ultramassive candidates seem too big, too early, as if some black holes skipped the baby phase and were born big. Seed black holes formed directly from collapsing gas clouds, or more speculatively, primordial black holes from the very early universe, born not from stars, but from the physics of space-time itself. Now let's pull back and see the whole ladder. At the bottom, stellar black holes. 300 solar masses, event horizons only a few kilometers to a few hundred kilometers across. City-sized, country-sized. Above them, intermediate mass black holes. Hundreds to hundreds of thousands of solar masses. Horizons from hundreds to hundreds of thousands of kilometers. From smaller than Earth to bigger than the Sun. Then supermassive black holes, 100,000 to 10 billion solar masses, event horizons millions to billions of kilometers wide, sitting in galaxy cores, sculpting their surroundings, and at the extreme end, ultramassive black holes, tens of billions of solar masses, shadows larger than planetary systems. Here's the twist. The larger the black hole's mass, the weaker the tidal forces at its horizon. Stand 300 kilometers above the horizon of a stellar black hole and you're stretched like spaghetti. Stand at the horizon of an ultramassive black hole and you might not feel anything unusual at all. You could cross the point of no return without noticing. The small ones kill you violently at a distance. The big ones let you in gently and never let you out. As Lena chases tiny wobbles in starlight and Aaron listens for faint space-time, whoops! Ada watches what these monsters do to their galaxies, because black holes don't just consume, they regulate. When gas falls into a supermassive black hole, it forms an accretion disk, a swirling, superheated ring of plasma. Magnetic fields twist and launch jets, beams of matter moving near light speed. These jets slam into the galaxy's gas, heating it, stirring it, sometimes blasting it right out of the galaxy. Star formation slows. The galaxy quenches. The mass of the central black hole correlates with how stars move in the galaxy's bulge. The M-sigma relation. Big black hole. Big effect. Black holes act like thermostats for galaxies. Too much. Cold gas. They feed and flare, pushing back. Too little? They nap. The size of the black hole in the middle helps decide how many stars, how many planets, how many chances for life a galaxy will get. Then in 2019, something happens that ties all of this together. For the first time, we see one. The Event Horizon Telescope releases the first image of a black hole's shadow, M87 Taus, a 6.5 billion solar mass black hole 55 million light-years away, a glowing orange ring around a dark center. The shadow isn't the event horizon itself, but the region where light is captured or bent away, about 2.6 times larger. For Lena, watching the press conference in the observatory lounge, it feels like seeing a ghost step out of a math textbook. For Aaron, it's like finally putting a face to the whoops he's been hearing. For Ada, it's a moment she pins above her desk next to her father's photo. "It's real," she whispers, "not just equations. We saw space-time missing where it should be." From city-sized stellar remnants to intermediate mass teenagers, we're just starting to detect, to ultramassive monsters steering the fates of galaxies. Black holes span a size range that's almost impossible to hold in your head. Yet, at first approximation, they're simple. A non-rotating, uncharged black hole is described by a single number, its mass. Add spin and charge, and you get two more, three numbers, to describe something that can swallow worlds. A 10 solar mass black hole and a 10 billion solar mass black hole obey the same basic equations. Only the scale changes. And that scale decides how violently they tear matter apart, how fast stars dance in their grip, how galaxies grow or stop growing, how many chances chemistry gets to become biology. Black holes, from stellar to ultramassive, aren't just things that eat everything. They're part of the universe's architecture. They may be one reason galaxies like ours and lives like ours can exist. If you could somehow stand outside the universe and look in, you'd see a web of galaxies lit by trillions of stars. At the hearts of many of them, tiny, bright cores where matter spirals into darkness. And at the center of each of those, a region of space-time so curved that even light bows out. We climb the ladder from stellar seeds to ultramassive gods. The strangest part? The same simple math describes them all. To people like Lena, Arun, and Ada, black holes aren't just monsters, they're characters, anchors around which everything else orbits. These things we once imagined as pure destroyers turn out to be essential to the way the universe writes its stories, including ours.